think, the Global Green Chem Innovation and Network Program is a great initiative for everybody to participate, to learn about green chemistry, and especially to apply green chemistry. And I'm very happy today to talk about a sustainability point of view towards hazardous chemicals, to put green chemistry a little bit into context. So first of all, let me say Selamat Datang. I'm very happy to share some of our thoughts about sustainability in general with you. And first of all, I think it's very important to talk about what sustainability really means for us and for everybody. And so sustainability per se is defined as meeting the needs of the present without compromising the ability of future generations to meet their own needs. And this is a definition that has been made by the United Nations Brundtland Commission in 1987. And if we talk about this definition of sustainability, it comes with some key circumstances that are certain, and that is very important to point that out, because we all have to understand, for this definition of sustainability, that resources are finite, resources should be used conservatively, and also that we have to consider long-term development priorities, and we have to consider the consequences of our resource use. So this is a really important baseline for the understanding of what sustainability really means for us. And the essence of sustainability is that we all want to lead comfortable lives. And of course, that's very valuable. And we also need to make sure that future generations can also lead comfortable lives. And we have to arrive to sort of a system where we can assure that. And there's a very important and very great saying that summarizes this very well, which is, we do not inherit the earth from our ancestors, we borrow it from our children. And only if we really use that saying for our understanding on how to do science and how to do chemistry, I think then we can really start using sustainable chemistry. And also, it's important to see where we are from an economic, from a societal, and from an environmental standpoint. So in the moment, we are sort of treating the economy, the society, and the environment as sort of separate, and we are starting to understand and starting to link those three parts together. And that is actually really a key to sustainability. And it's also very important to understand that sustainability is more than just quality of life. It's actually a balance between economic endeavors, society endeavors, and of course the environment. And an ideal scenario where we really need to be in the future is the following. So of course, economy is entirely embedded in society. And so it's entirely embedded in society, and all human economy or economic activity requires interaction among people. But then society is also much more than economy and encompasses social contacts, arts, religion, and ethics. And those are not necessarily directly linked to economic activities. And then, of course, society forms part of the environment just as everything else does. And I think only if we really think about how we can reach this ideal scenario, can we also do a chemical industry that is more sustainable with our planet, with our society, and that will also bring us economic benefits as we need them. And in this moment, let me give you a little bit of a snapshot of chemistry, how we do it in the moment. Of course, when we do chemistry, we're always doing chemistry with an intention. And the intention of chemistry is, of course, to produce something that fulfills a function. And this function can be either that we're generating colors or pigments, or we're generating useful material like plastics to make bottles or other containers. We also have a chemical industry that can develop potent drugs to help us to overcome diseases. We can also generate high-tech components, food additives to protect our crops. So there's a lot of different functions that we can fulfill with chemistry. But then on the other hand, chemistry, as we have seen in the past, always brings consequences, and many of those consequences are negative. And here we can see a couple of examples. Usually chemistry is hard on our waters, and we have seen for decades now that we are contaminating our water with chemicals that we are using, and also the chemicals that are liberated from chemical industries. We are also using natural resources on a level that is not sustainable with the environment of our planet. We're also just using chemicals to maximize profit. We're accumulating a lot of waste, like plastic, for example. We have chemical plants that are prone to accidents. And finally, we are also using processes and materials that cause climate change. And well, of course, all those consequences come from the risks of the chemistry that we are doing. And I just want to show you a couple of very that have happened because of poor management of risks and hazards. One was this explosion in Lebanon in August 2020, where due to storage of explosive ammonium nitrate, storage under really bad circumstances in a non-ventilated area, a non-adequate area, 2,750 tons of this material exploded, and almost 220 people died, and more than 7,000 people were injured. And this accident was really one of the most recent cases of a drastic chemical accident that was caused due to bad management of a material that has been confiscated 6 years prior to the explosion from a ship and hasn't been treated after that. So that was a really big case of bad management that led to inherent danger of the situation and led to this tragic accident. And another recent example is actually an example from the United States, where in February 2023, a freight train caught fire, a freight train that was actually carrying a lot of different chemicals. And this freight train caught fire, and more than 50 cars of the train generated a derailment pile and started burning at the site for several days. And this was also due to a negligence of the train, of course, and the train had to be burned off because there was vinyl chloride on the train, and when you leave vinyl chloride under heat, it can lead to explosive polymerization. So that's why the agencies that were trying to solve the problem started burning off the vinyl chloride in a controlled way. But then, of course, here you can see the cloud of burning residue that was generated and contaminated the air, soil, and waterways in 16 states in the United States. And of course, this was very recent, so the long-term effects on all the waterways and the air quality and also on human health are still largely unknown. And as I mentioned previously, these events, and usually also other tragic chemical events, chemical accidents, are the result of bad management of risk and hazards of chemicals. And it's important to understand where risk and hazard sort of interplay. First of all, of course, we all know the old saying that everything is toxic. It simply depends on the dose. And here you can see a picture of the old chemist Paracelsus, and he phrased this usually as the dose makes the poison. So whatever we use in a chemical lab or in a chemical process will be poisonous if the dose is high enough. But then it's important to understand how risk, hazard, and exposure are actually interlinked. So the risk of a chemical reaction or a chemical accident is actually due to the hazard of the compounds or of the process per se that we are conducting, and the exposure to the chemicals in it. And of course, it's very interesting to think about developing chemicals that are not hazardous, because if we focus on reducing risk by reducing the inherent hazard, then the exposure to it becomes irrelevant. So if we are developing chemicals that are not dangerous anymore, we can be exposed to them, and that wouldn't really cause anything. But of course, what the chemical industry or chemical research has been focused about until now is conventional approach to deal with hazards and substances that are hazardous by reducing the risk, by minimizing the exposure. And of course, that means that we can go to a lab and wear personal protective equipment or ventilation if the chemical is volatile. But then we are still not reducing the risk of accidents. For example, the train derailment in the US, of course, it's a train that goes outside in fresh air, and per se, it's not dangerous. But then, of course, accidents can happen, and then exposure can also happen. So how can we actually work on reducing the risk by reducing the hazard of the chemical that we are actually using or transporting in this case? Because if there is no hazard, then exposure becomes irrelevant, as I already mentioned before. And why does a chemical have to be volatile or toxic? So this brings us to one of the underlying hypotheses of green chemistry, which is, of course, one of the major focuses of the Global Green Chem Innovation and Network Program. And this is, if we can master the design and synthesis of molecules, why don't we aim towards eliminating the hazard per se? And this is actually a little bit of a change of perspective, of course, because hazard, if you think about all the chemicals that we have developed over the last decades or centuries, hazard must simply be recognized as a flaw in the design process. Of course, a chemical is only dangerous because we haven't thought about developing a non-dangerous compound that maybe fulfills the same function as the chemical that is dangerous. So green chemistry moves our consideration of how to deal with environmental problems from the circumstances of the use, of the exposure, of the handling, of the treatment, of protecting against recycling, of the costs of dangerous chemicals, hazardous chemicals, to the intrinsic. So the intrinsic meaning we can design or redesign a molecule so that it has reduced toxicity. We can reduce the ability of the molecule to manifest the hazard. We have the knowledge, we have the tools to analyze the hazards of a chemical. We understand why it is hazardous, and we can actually work on developing alternatives to it. We can also work on inherent degradability or recyclability, and also the inherent safety from accident, of course, comes to pass with it. And we also understand very well which chemical compounds are profitable, which are not. And green chemistry really comes at this from a little bit of a wider angle, really tries to intrinsically design chemicals and chemical processes so that they are more sustainable for the environment, and of course also for human health and environmental health. So it's really, I want to summarize this with a call, or not a call, but suggesting that we have to understand that it's time for a change, of course. So we need to fulfill, of course, all the functions that we have to fulfill with chemicals. But we also have to eliminate all the risks that we have sort of negotiated until now, because the reductionist approach, the old approach on how to do chemistry, the non-green chemistry approach is we'll fulfill the function, we'll negotiate the risk, and think about the rest later. But we have to change this because, first of all, there are always alternatives, because nature fulfills all the chemical functions or to us humans. So green chemistry really comes from the need for a change, and also from the endless possibilities, for example, that nature brings to us. And I know that today's event will go through various different aspects of green chemistry, and I think you're going to see some fantastic alternatives where green chemistry has been applied already. And this is really just to sort of set the tone for what's coming in this event. And let me finalize by thanking you, and thanking you for organizing this great event, thanking Universitas Pertamina and all the green chemistry team for participating in this Global Green Chem Innovation and Network Program. And I would be happy to answer a couple of questions. And if there are no questions, then I wish you all a fantastic event. And I think everybody will learn a lot about green chemistry. And this project has just started, so we are very excited here at Yale University to work with you over the next years and bring this project off the ground, work a lot on the accelerator programs that are very exciting that you will probably hear about today, and also about the implementation of green chemistry in the industrial sectors. So terima kasih, thank you very much, and I'm open for any questions should you have some, and feel free to reach out to us on any of these channels. Thank you very much.
Kepada Bapak dan Ibu yang ingin menyampaikan pertanyaan, ya silahkan, mungkin panitia bisa dibantu, silahkan Ibu untuk menyebutkan nama dan instansi serta pertanyaan.
Hello, my name is Dian. So I come from Unilever Oleochemical Indonesia. Maybe just one thing that quite interesting that you mentioned your focus. The focus is to make zero hazard for all chemicals. So if you can share what is the status today, for example, like we know that there is a lot of hazardous chemicals in the world, chemical for the pharma, etc. So can you share what is the focus in the world today? Because we know that we cannot achieve for all, but we can start with one to another. So if you can share what is the what you have done today for doing. Thank you.
Thank you very much for that question. A very, very important, very, very big question. So maybe I can share a little bit about what is maybe also the essence of this program, which you might have heard about, the persistent organic pollutants. So those chemicals, for example, are chemicals that are persistent in nature, and nowadays a lot of alternatives for those chemicals have been developed. So persistent organic pollutants, for example, DDT, which was a chemical that has been used a lot in the 1950s and 1960s to control mosquitoes. And with permanent chemical development, new chemicals are always developed in the moment, or permanently developed new developments are always there. So that's maybe a little bit about the essence of the Global Green Chem Innovation Network Program, all those persistent organic pollutants. And I can also share maybe a little bit about things that we are doing here in the university. So we are focusing a little bit more on materials, but because in the end, if you think about materials like plastics, they are also hazardous because they don't degrade in nature, and we have our environment, of course, filled with plastic, microplastic, nanoplastic. And what is a big trend now in chemical research is actually finding plastics, materials that still fulfill the function of a plastic, but that are designed from the beginning to be fully biodegradable, and they will degrade to molecules that don't accumulate anywhere in nature. So a good example is PLA, polylactic acid. That's a biopolymer, so to say. It comes from cellulose byproducts, and it will biodegrade into cellulose byproducts. So that's also a very interesting approach, how to make new materials that we can still use with all the machinery that the materials industry has nowadays, but that are designed from the beginning thought to be biodegradable and non-persistent and non-dangerous. And then the same, of course, is also true for pesticides, for example. Pesticides, of course, many of the pesticides that have been used over the last decades, some of them are also persistent, and now there are many companies that use a little bit different approaches that don't do chemical pesticides anymore, but they work on peptide-based pesticides or pheromone-based pesticides, and those are, of course, all molecules of biological origin, and they will be biodegradable per definition, and much less problematic for our water quality or also for the quality of the soil. I hope that answers the question a little bit. I think it's a really fantastic point to discuss all that, and we could spend hours on discussing different aspects of chemicals that are developed nowadays, but this is just to give you a little bit of a bigger picture overview.
All right, thank you very much, Mr. Lars Ratjen. Ya, beri tepuk tangan sekali lagi untuk Mr. Lars. Rekan-rekan,